Saxon Algebra 1, lesson 87. It's a great day for an algebra lesson. I am excited. Have you noticed I'm always excited about the lessons? Because I love them all. They're so fun. There's some that annoy me, but most of them I think are delightful. This one is a two-parter. We're going to talk about systems of equations and bump it up to be just a little bit harder, but let me remind you of what we already know. We have solved a lot of systems of equations that look something like this. Right? Got the little bracket on there. That's how we know it's a system. Quote unquote, a system means that we're looking for a value for x and a value for y that will make both of these statements come true. We also know that we could graph both of these as lines, and where they crossed, that would be the value for x and the value for y that will make both of them come true. All right, now this is an equation that's all set up for substitution because we see that this one is y equals, a second, I don't like where my light is. It's making a shadow of my hand. And this has got a y in it. We can take this and plug it in right here and then solve, right? Well, we're going to use that same general strategy on something that looks more complicated. Here's the first example. In this one, we have 4 equations. Let me write them out to you. At first, you're going to be somewhat horrified, I think. This is a system of equations. I'll give you a second longer to copy it. I know I go too fast, don't I? Okay, let me give you just a little bit of information. Later we will be working word problems with all of these, and then the words will make more sense. The R and the T, the R stands for rate, and the T stands for time, and the subscripts, these little letters down at the bottom, they equal names. These will be stories about people taking trips, maybe, you know, Elsie and Wilbur. I just made those names up. But this will be the initials of the person who is having this adventure. So later it will make sense. Now, the letters will make more sense later. Now let's just look at the equations and just trust that these clumpy things make sense. Remember, the little letters just go with the big letters. They're not separate variables. They're just like two-part names for the variables. So the variables, we can look at the big letters. What we see is there are 4 variables here, right? 1, 2, 3, 4. And then here, we have one of the variables with a number, another variable with a number. Okay, so we can do some substitution, right? We can put this RE in here, and we can put this RW in there. Now, what do we do with this last one? The problem with this last equation is that it's not set up like this, right? It's more like this where the x and the y are together. We want it to look more like that. Well, we know how to fix that, right? Just subtract one of these or the other, it doesn't matter which, to the other side. So we'll change it to be, let's just bump the TW. So I'll make it TE equals 9 minus TW. So we're just gonna rearrange this a bit. And now this will go in here. By the way, this equation has a special name. I'm putting a star by it. It's called a base equation. We use it as the base, and we plug the other equations into it. How do we know it's the base equation? Because it has the most variables, right? This only has 1, this has 1, this has 2. But this one, and John almost always helps us out by writing it at the top of the list, this one includes all the different letters. So that's how we know it's the base equation. It's that straightforward. All right? So now what we're ready to do is step 1, we write the base equation in buckets, or with buckets, I guess would be a better way to say that. So every one of these variables we're going to write as a bucket. R-E-T-E equals, and then 2 more variables after. We just copy the shape of it, only instead of putting in the letters, we just leave them blank. We put in buckets. Now, we're going to substitute in the other equations. Okay, just like we would do here where we put that in there. We're going to, let's see, this first space is for R sub E. That's the number 200. This one is R sub W. Okay, that's the first one on the other side, and it's 250. We fix this one, TE, so that's over here. That should be 9 minus TW. T sub W is a better way to say it. And then this last one, we don't have anything to write in. So what we do is we just put in the variable that lives there. And when we do, we notice something cool. This is a T sub W. This is a T sub W. Oh, they match. That's really cool. That means we'll be able to solve it. And that is our third step, is to solve. Where should I write that? I guess I'll write it here. Okay, this part's straightforward. We've done a lot of this. So now what I'm gonna do is I'm gonna see, okay, here I've got a distribution. Here I don't have a distribution. I can just take the parentheses off. So let's go back here and distribute. 200 times 9 is 1,800 minus 200t equals 200 and, oh, TW, sorry. T sub W, right? Those two I can just write together. These I distribute. All right, now straight algebra, I'm gonna add this 200 TW to the other side. Swim it across, right? Cancels there. And I get 1,800 equals 450 TW. I'm gonna copy this up to the top of the next page. We're almost there, right? Divide both sides by 450. Now, how do we do that? Whoops, 450. What I think of is, can I just figure out how many times 450 goes into this? 2 450s together will make a 900. 2 900s will make 1,800. That tells me that 1,800 divided by 450 equals 4. So, T sub W equals 4. And then I go back here and go, okay, I have to solve for TE as well. And look what we have. TE equals 9 minus TW. Whoops, I made that too big. That should be a little baby one. And we know that TW is 4, so TE equals 9 minus 4. So TE equals 5. Ba-dum-bum. There we go. That's the right answer. All right. So the trick to this is to figure out what your base equation is. Let me go back and show you again the problem. We have to identify our base equation. We have to make sure that all 3 are ready to plug in. The 2 rate values are usually straightforward. Time is often written, the 2 time variables are written as a sum. And so we just have to rearrange and get one by itself. Then we plug in, be sure you use buckets so that you don't mess it up. Promise me, I'm going to save you time and trouble if you do it my way. And then just solve. All right, we have one more like this. I'm gonna start on a fresh page. It is example 87.2. And here's John's information given. Now this is our first equation, so we can guess it's probably our base equation. But what we notice is instead of having letters, we have numbers as subscripts. Same difference, it doesn't matter. This time they're being added together, multiplied and then added to equal a number. That's fine. It looks a little different than last time, but it will not hurt us. Our 1 equals 30, our 2 equals 40, and T1 plus T2 equals 10. That is our system that we're trying to solve. That is a really bad parenthesis. I'm just double checking my numbers. Beautiful. Okay, so again, we look for the base equation. Spoilers, it's almost always at the top, but we can just check and make sure, yeah, these are all, this is a number, and then a sum, just like last time. So this is our base equation. I'm gonna rearrange this first. Which one should we kick over? Let's subtract T1 this time. So we'll say T2 equals 10 minus T1. Okay, we'll just mix it up. Now, write the base equation with buckets. So it's gonna be that, right? Every letter, every variable turns into a bucket. We copy the same shape. Now we plug in what we know. Here's a 30, here's a 40, and then T2, which is in the second clump, is 10 minus T1. And if we don't have anything for one of the variables, then we just put the letter back in. And this is what should always happen. Look, we get T1s for both. Beautiful. Distribute here. Once we get it written in, now we can start getting rid of the parentheses. Here we don't need them. We can just write 30 T1 plus 400 minus 40 T1 equals 360. We can combine these like terms at the same time we subtract the 400. Doing the steps together to save us a little time. 30t minus 40t is going to be minus 10t sub 1 equals minus 40, which looks scary, but a few minus signs never hurt anybody, right? That cancels, and we get t1 equals positive 4. Hey, that's the same answer we got last time, right? And then we know that they have to add up to 10. So we know that T2 has to equal 6. Now, last time when we did the problem, I actually showed the work, right? I wrote this out and substituted it in. That's kind of pushing our need for detail. It's pretty obvious that we can do that in our head. What I like to do though is I show this as the answer, and then I just write 10 down here. And it's just a nice way of showing, oh look, there's the 10 that they add up to, right? It's just a nice little check that we can build in. Okay, so these are more advanced systems of equations. We're gonna be working a lot of problems that have this kind of a setup, and so you'll get lots of chances to practice. Okay, part B. Flip of the page. We're going to talk a little bit more about functions, just a little bit. We're going to talk about what we call tests for functions. Now, we've already talked about this a bit. We've talked about the fact that you can take inputs and then you can show some function. Let's just make it x minus 2. And then we have an output, right? We call this the input, and this the output. And we can choose numbers here and run them through. But John has this shorthand way of showing it, what I call the ovals test. That is not John's name, that is my name, because he does something like this. He doesn't show us the function, he just gives us some inputs, and then he gives us some outputs, and he does this thing where he draws the line that connects them. And we can tell if every number on the input side has one and only one partner on the output side, then it's a function, right? We call it a one-on-one matching, we call it a mirroring, we call it an imaging. Every input has one and only one output. That's how we know that it's a function, right? I'm going to write this out. You know how words fail us. Right? So every input has one and only one image or output. All right, so that's the first kind of test. The second kind of test I'm going to write over here, and this is called the pairs test. Again, I made up these names. Because what we can do is we can use these same numbers to create ordered pairs, right? And the rule is exactly the same for the pairs test. Every input has one and only one image or output, right? It works exactly the same. We look at the first ones. If there are no repeats, we're done. We don't even have to look any further. But if any of the first numbers, the x's, the inputs, whatever you want to call them, they have many names. If we repeat any of those, then we have to check and make sure that they always are matched to the same one, right? So this rule works the same on this side. It's the same rule, okay? These are the tests that we've already looked at and that you've worked on. There is a third test. Here it comes. Are you pumped? It is called the vertical line test, and John does call it that. And this is a test we use when we actually graph the function. Now, we're not going to do a ton of graphing of these functions yet because it's a little bit beyond our pay grade for now. But let's just say that we graphed a function that looked like this. And we will get to that in advanced mathematics. We will graph functions like this. Or we'll graph equations like this, and we want to know, is this a legitimate function? And this is how we test. I'm going to grab a different color so it's easier to see. What we do is you can do it with an actual pen, but you can do it visually, mentally too. We practice drawing lines, vertical lines up and down, and we look to see how many times that vertical line crosses our wannabe function, right? So what I'm doing is I'm putting a dot where each one of my vertical lines crossed the function that we drew. And what I see is that each line only touches the function at one point. And let's pretend it keeps going, right? But from what I see here, this passes the vertical line test. So now I'm going to write it out in words. I'll let you copy that. It's so much easier to understand than it is to explain it in words. If any vertical line touches the function at no more than 1 point. So if it doesn't touch it at all, that's okay. What we don't want is a vertical line that touches our function in more than 1 point. If it's no more than 1 point, it's a function. So this one is a function. So we're gonna give it a very happy face. And I'm gonna write valid function right there. Okay, let's try another one. This one is another thing that we'll learn to graph later on, but you already know it. It is a circle. Okay, so now we practice our vertical line test. We just start drawing some vertical lines. Well, here's one, and here's another that don't touch the function at all. So they're okay. They touch it at only, at no more than 1 point, right? 0 is no more than 1. And we could also draw a line, pretend it's perfect, that comes and just touches at one little point right there. We could draw another one over here, right? Pretend it's perfect. One little point right there. That would be okay. But we can easily see that there are a whole bunch of vertical lines that would come through and that would hit it at 2 points. Uh-oh, our test just failed. So we have to say that this one is a fail. So it is an invalid function. It's okay if your brain is a little wobbly on why that's exactly true. I just want to make sure that you understand the mechanics of how to draw the lines and see, do they cross my picture in more than one place? If so, fail. All right, so this is called the vertical line test, and it's a new way, it's a third way to know whether or not the numbers we've been shown, or the graph we've been shown, represent a valid function. Yay! And John gives us one more problem. It's easier just to show you than to copy. So we're gonna look and see if these graphs represent a valid function. So we just imagine, can we draw a vertical line that touches more than once? Yeah, we definitely can for this one, right? Look, the y-axis hits it 1, 2, 3 times. No bueno. How about this one? Well, this one looks pretty good, right? This one looks like it curves enough that it's not going straight down. It looks like it keeps curving. So this one looks like a valid function. This one, ooh, no. No bueno, right? Look at, again, the y-axis helps us out. It crosses it twice. So these are the way we approach this vertical line test of a function. We already did the other two, the ovals and the pairs test. We did those in the other lesson, but John saved this third test, which I think is the easiest of all, for a separate lesson. This was a no, this was a yes, this was a no. All right, and you can see here for your practice, you get to do some too, yay. Look, here's one kind of like what I drew. Spoilers! Okay, guess what? Lesson 87 is complete, yay! Thank you, I hope you enjoyed it. Goodbye.